There is a moment in every scientist's life, sometimes early, sometimes late, when the tools stop feeling like tools and start feeling like something stranger. A physicist writes down an equation to describe the arc of a thrown stone and finds the same equation, with no alteration, describes the orbit of a planet. A biologist borrows a formula from thermodynamics to model the flow of energy through an ecosystem, and it fits. A mathematician, working in perfect isolation from anything physical, invents a structure of pure thought, a geometry of curved surfaces, say, or an algebra of imaginary numbers, and decades later a physicist discovers that this invented structure is the exact language nature uses to organize itself at the deepest level. Why? This is the question that haunted Eugene Wigner, the Hungarian-born Nobel laureate, when he sat down in 1960 to write an essay that has troubled the philosophy of science ever since. He called it "The Unreasonable Effectiveness of Mathematics in the Natural Sciences," and his thesis was disarmingly simple: the correspondence between the abstract structures of mathematics and the concrete structures of the physical world is so precise, so far-reaching, and so persistent that it demands explanation, and no one has one. Wigner was not exaggerating. Complex numbers, invented in the 16th century to solve a puzzle about cubic equations, turned out to be the indispensable language of quantum mechanics 300 years later. Riemannian geometry, developed by Bernard Riemann in 1854 as a purely intellectual exercise in imagining curved spaces, became the scaffolding of Einstein's general relativity 60 years later. Group theory, born from a young Frenchman's study of which polynomial equations can be solved by radicals, now provides the foundational framework for the standard model of particle physics, our deepest account of the forces and particles that constitute matter. These are not isolated coincidences. They form a pattern, and the pattern intensifies as science deepens. The more precisely we probe the universe, the more precisely mathematics describes what we find. The prediction of the positron, the antimatter twin of the electron, came not from an experiment but from a minus sign in an equation. The existence of the Higgs boson was anticipated by mathematical structures decades before any collider was powerful enough to produce it. The bending of light by gravity, the quantized energy levels of atoms, the exact value of the magnetic moment of the electron to 12 decimal places, all were predicted by mathematics and then confirmed by observation. Wigner called this correspondence a gift we neither understood nor deserved. He offered no solution. He simply named the mystery and left it open, like a door into a room no one has yet fully explored. This book is an attempt to walk through that door. The answer it proposes is not that the universe is secretly made of mathematics, though some have argued this. It is not that mathematics is merely a human invention that we project onto the world, though there is truth in this too. The answer is at once simpler and more surprising. Mathematics describes the world because the world is made of things that last, and lasting, it turns out, has a structure. The structure is mathematical, not by choice or coincidence, but by necessity. Think of it this way: the universe is a torrent of change. Particles collide, stars ignite and collapse, species evolve and go extinct, civilizations rise and fall. In this torrent, some things endure. An atom of gold has persisted for billions of years. A hydrogen atom has persisted since the first minutes after the Big Bang. The laws of physics themselves, the rules that govern what changes and what does not, have persisted, as far as we can tell, since the beginning of time. What does it take to endure? This is the question at the heart of this book, and the answer, developed with full formal rigor in the academic paper included at the end of this volume, Kriger, 2026, DOI colon 10.5281/Zenodo.xxxxx, is that endurance requires invariance.